How fast are you moving right now? The answer you feel a comforting and absolute zero is perhaps the most profound illusion in the entire universe. It's a quiet lie we tell ourselves every moment of every day, a fiction born from the gentle, unyielding cradle of Earth's gravity. You're sitting, standing, resting, yet you are on a journey of unimaginable violence and speed. Right now, this planet, this familiar sphere of rock and water, is spinning on its axis at over 1,000 miles an hour, a dizzying pirouette that we are utterly oblivious to. But that is merely the first innermost gear in a celestial machine of staggering complexity and velocity. Our Earth in its silent, faithful orbit is hurtling around the Sun at 67,000 miles per hour. That's a speed that could cross a continent in under 3 minutes, a velocity so immense that our minds struggle to grasp it as anything other than a sterile number on a page. We don't feel the cosmic wind in our hair. We don't sense the sheer propulsive force required to keep 8 billion souls tethered to this cannonball of a world. We simply watch the seasons turn, a gentle consequence of this frantic cosmic race. Yet even this incredible speed pales in comparison to the next scale of our journey. Our entire solar system, a tiny glittering raft with the Sun as its masthead, is itself a passenger on a far grander vessel. We are embedded within one of the spiral arms of our home galaxy, the Milky Way, and we are being swept along in its majestic, ponderous rotation. At our location, some 26,000 light-years from the galactic core, we are careening through interstellar space at nearly 500,000 miles per hour. Think of it every hour that passes you. Your home, your entire civilization have travelled a distance equal to traversing the Earth 20 times over. We are all unwitting astronauts on a starship of colossal proportions, a swirling metropolis of 400 billion suns, and its voyage is the grandest story of them all. For generations we believed we understood the basic contours of this journey. The Milky Way, this magnificent island of light, drifts through the intergalactic medium carried along by the most fundamental force in the cosmos, the expansion of the universe itself. We pictured our galaxy and its neighbours as leaves on the surface of a uniformly expanding river, each one moving away from the other as the fabric of space-time stretches relentlessly outward, a process set in motion by the Big Bang nearly 14 billion years ago. This is the baseline, the expected, the orderly cosmic flow that should dictate our ultimate trajectory through the void. It's a clean, elegant model that accounts for the grandest observation in cosmology, that everything is on average moving away from everything else. To confirm this, to measure our true motion against the backdrop of the universe, we needed a fixed point, a universal signpost against which all movement could be judged. For a long time, such a concept seemed impossible. In space, everything is relative. There is no absolute up or down, no definitive north or south. How could we ever know our true velocity if every star, every galaxy we measured against was itself in motion? The answer, when it came, was not found in a distant quasar or a stable nebula. It was discovered as a whisper, a faint ethereal hum that permeates every cubic inch of the cosmos, a relic from the very dawn of time. It is the cosmic microwave background radiation, the CMB. This is not light from stars. It is something far more ancient, far more profound. It is the afterglow of creation itself, the fading warmth of the Big Bang cooled over billions of years of cosmic expansion to a mere 3 degrees above absolute zero. This ghostly light, released when the universe was just a few 100,000 years old, provides the ultimate frame of reference. It is a snapshot of the infant cosmos, and because it was emitted from everywhere at once, it is astonishingly uniform in all directions. It is the closest thing we have to a state of absolute rest. Imagine standing in the centre of a room where the walls, floor and ceiling are all glowing with a perfectly even faint light. If you stand still, the light you perceive from every direction will have the same temperature. But if you begin to run the light in front of you, will appear slightly brighter, slightly hotter, as you rush into its waves, a phenomenon known as a blue shift. The light behind you, in contrast, will appear fainter and cooler as you race away from its waves, a red shift. By building exquisitely sensitive instruments and pointing them to the heavens, we have measured this temperature difference in the cosmic microwave background. We have seen our own motion etched into the oldest light in the universe. One side of our sky is infinitesimally warmer, the other infinitesimally cooler. The pattern is undeniable. It is our cosmic speedometer, and it tells a story that is both awe-inspiring and deeply unsettling. The reading is unambiguous. Our entire local group of galaxies with the Milky Way and Andromeda at its heart is hurtling through space at a staggering 1.4 million miles per hour relative to the rest of the universe. That's 630 kilometers every single second, an incomprehensible, relentless velocity. A portion of this speed, of course, is expected. It is the simple consequence of cosmic expansion, the majestic outward flow of the universe. But when astronomers meticulously subtracted the effects of that expansion, when they calculated the speed we should have from the Hubble flow, they were left with a profound and disturbing discrepancy. There was something else. An extra and enormous component to our velocity. A peculiar velocity. They called it a motion that cannot be explained by the simple, elegant expansion of space-time alone. It's as if we are on a cosmic river, but a powerful, unseen current is pulling us sideways, dragging us off course with irresistible force. Our galaxy is not just drifting, it is being propelled. The direction of this peculiar motion is just as mysterious as its speed. It points us towards a specific patch of the southern sky, towards the constellations of Centaurus and Hydra. For decades, the prime suspect for this cosmic summons was gravity, and the search for the source of that gravity became one of the great detective stories in modern astronomy. The prevailing theory was simple: somewhere out there in that specific direction must lie an immense concentration of mass, a gravitational behemoth whose pull is so powerful it can capture and redirect the flight of entire galaxies, including our own. The hunt was on for what came to be known as the Great Attractor. Astronomers scanned the heavens, mapping the three-dimensional positions of tens of thousands of galaxies, trying to trace the gravitational contours of the local universe. They were building a map not of light, but of mass. They found filaments of galaxies stretching for hundreds of millions of light-years, great walls and superclusters, forming a vast, intricate cosmic web. And in the centre of the Laniakea Supercluster, our own celestial neighbourhood, they found it. A region of space teeming with ancient galaxies, a place where the gravity of 1,000 Milky Ways is concentrated, lurking some 150 million light-years away. This surely was our culprit. This was the Great Attractor, the cosmic anchor, pulling us inexorably toward it. It was a beautiful solution, a testament to the power of gravity to sculpt the cosmos. But as our maps grew more detailed, as our measurements became more precise, a nagging problem emerged. The Great Attractor, as massive as it is, simply wasn't massive enough. Its gravitational pull could only account for a fraction of our peculiar velocity. There was still a huge, unexplained component to our motion, so the search widened. Astronomers looked even deeper past the Great Attractor and found an even larger structure, a colossal river of galaxies called the Shapley Supercluster, located more than 600 million light-years away. This was one of the most massive concentrations of matter in the known universe, a true gravitational leviathan. Its pull, even from that immense distance, is palpable, and it certainly contributes to our vector. Yet even when you combine the gravitational pull of the Great Attractor with the distant tug of the Shapley Supercluster, even when you account for every known galaxy cluster and filament in our vicinity, the numbers still don't add up. The equation remains unbalanced. Our galaxy is still moving too fast. It's like feeling a powerful wind at your back but turning around to find the air perfectly still. The force is real, its effects are measurable, but its source remains infuriatingly elusive. The greatest minds in cosmology were faced with a stark reality. The celestial attractions we could see were not enough. Something else was at play. Something was missing from our understanding of the cosmic dance. For years we searched for more mass, for a hidden attractor, a cloaked cluster of galaxies that could solve the riddle. But what if we were looking for the wrong thing entirely? What if the answer wasn't about what was pulling us, but about what was behind us? Science often progresses by inverting the question. We assume gravity is a force of attraction, a cosmic tether that pulls things together, and it is. But in the grand arena of the cosmos, the absence of gravity can be just as powerful as its presence. Imagine a vast, perfectly balanced tug-of-war with equal teams pulling on a rope in all directions. The rope stays perfectly still. Now what happens if one team suddenly lets go? The rope doesn't just sit there. It lurches violently in the opposite direction, not because of a new pull, but because of a sudden profound imbalance. The absence of a force in one direction has created a net acceleration in the other. This is the radical, counterintuitive idea that has reshaped our understanding of our place in the universe. As astronomers mapped the cosmos, they found not only clusters and walls of galaxies, but also the opposite vast, almost incomprehensibly empty regions where galaxies are hauntingly scarce. They discovered cosmic voids, enormous bubbles of near-nothingness, some stretching for hundreds of millions of light-years across. These are the quiet, dark and forgotten places in the universe, the spaces between the glittering filaments of the cosmic web. And as we plotted our Milky Way's trajectory on this new, more complete map, we made a startling discovery. While we are being pulled towards the Great Attractor and the Shapley concentration in front of us, we are also positioned at the edge of one of these immense cosmic deserts. Directly behind us lies a region of profound emptiness. It's called the local void. This is not an object, it is an absence. A cavernous underdensity in the fabric of space-time, a place where for billions of years gravity has been weaker than everywhere else around it. It is a valley in the landscape of mass, a gravitational dead zone. And just as a mountain pulls things toward it, a valley effectively pushes them away. The local void doesn't exert a force in the conventional sense. It is not emitting some mysterious anti-gravity field. Its power comes from what isn't there. For eons, the region of space that would become the local void has been losing matter, its sparse collection of galaxies being pulled away towards the denser structures on its periphery. As this region emptied out, it created a gravitational imbalance across the cosmos. Galaxies near its edge, like our own Milky Way, feel a stronger gravitational tug from the dense regions in front of them than they do from the empty void behind them. The result is a net push away from the emptiness. It is a repulsive shadow cast across half the sky, a silent and invisible engine that has been accelerating our galaxy for billions of years. This discovery was a paradigm shift. The mystery of our peculiar velocity was not just a story of attraction. It was a story of repulsion, a tale of two forces acting in concert, a cosmic pull from the great cities of galaxies that lie before us, and an equally potent cosmic push from the great empty plains of the void at our back. This vast expanse of nothing, this ghost on the cosmic stage, may hold the missing key to understanding our galaxy's relentless, inexplicable journey through the dark. It is a force defined not by what it is, but by what it is not. And its influence on our ultimate destiny is something we're only now beginning to comprehend. Undefined. You feel perfectly still right now, don't you? Perhaps you're sitting in a chair, grounded by the familiar and reassuring pull of the earth. But that sensation of stability is a profound illusion, a gentle lie told to us by our limited human perspective. The chair, the room, the very ground beneath you, it is all hurtling through the cosmos on an unimaginable journey. Your planet spins on its axis at over 1,000 miles per hour, a dizzying pirouette that we have learned to ignore. That spinning Earth orbits the Sun, a steadfast passenger, on a celestial carousel travelling at an astonishing 67,000 miles per hour. Even our Sun is not the stationary heart of the universe we once imagined it to be. It, along with our entire solar system, is being dragged on a grand tour around the Milky Way's core, completing one vast circuit every 230 million years. This is the journey we know, the motion we can calculate. But this is only the beginning of the story. Beyond these nested cycles of movement lies a deeper, more mysterious current, a motion that is not our own, a velocity that has nothing to do with orbits or rotations. It is a vector pointing toward an unknown destination, a speed that for decades has baffled the brightest minds in astronomy. To understand this motion, we must first rewind the cosmic clock back to a time when we believed our galaxy was an island drifting alone in an eternal, static and silent universe. That comfortable silence was shattered not by a sound, but by light. In the 1920s, high on a lonely peak in Southern California, a revolution was brewing inside the cold steel dome of the Mount Wilson Observatory. Here, the astronomer Edwin Hubble, a man as meticulous as he was ambitious, was undertaking a laborious cosmic census. Night after night, he guided the colossal 100-inch Hooker telescope, then the largest eye on Earth toward faint ethereal smudges of light, the so-called spiral nebulae that peppered the deepest photographic plates. For years, a great debate had raged. Were these smudges mere clouds of gas within our own Milky Way, or were they, as some dared to imagine, entire island universes, galaxies in their own right? Unimaginably distant Hubble's quest was to measure their distance to settle the argument once and for all. His tool was a special class of star, a celestial lighthouse called a Cepheid variable. These stars possess a remarkable quality. They pulsate brightening and dimming with a precise clockwork rhythm, and the speed of that rhythm is directly linked to their true intrinsic brightness. By comparing a Cepheid's true brightness to how dim it appeared from Earth, Hubble could calculate its distance with unprecedented accuracy. It was painstaking, grueling work. He would expose fragile glass photographic plates for hours on end, chilled to the bone in the unheated dome, capturing the faint glimmer of these cosmic candles. And in 1923 he found one, a single pulsating point of light within the Great Andromeda Nebula. He did the calculation, then he checked it, and checked it again. The number that stared back at him was staggering. Andromeda was not a nearby cloud. It was nearly 1 million light-years away, a colossal island of stars completely separate from our own. In a single moment, the known universe expanded by an almost infinite factor. Our galaxy was not alone. It was just one of countless others in a truly vast cosmos. But this discovery, as monumental as it was merely the prelude to an even greater revelation. Hubble, along with his contemporary Vesto Slipher, wasn't just measuring distance. He was also analysing the very quality of the light arriving from these distant galaxies. He passed their light through a prism, a spectrograph, spreading it out into a rainbow of constituent colours, a unique barcode for each galaxy. And in these cosmic barcodes he noticed a strange and persistent pattern. The characteristic spectral lines of known elements like hydrogen and calcium were not where they were supposed to be. In nearly every galaxy he observed these lines were shifted toward the red end of the spectrum. This phenomenon known as redshift had a clear and unambiguous physical meaning. The source of the light was moving away from the observer. The more dramatic the shift, the faster it was receding. What Hubble found was not just that a few galaxies were moving away, but that almost all of them were. And when he plotted their speed against their distance, the result was a revelation that would forever alter our place in the universe. The farther away a galaxy was, the faster it was speeding away from us. The relationship was undeniable, a straight line on a graph that pointed to a breathtaking conclusion. This wasn't a chaotic scattering of galaxies fleeing from a central point. This was something far more profound. The very fabric of space itself was expanding. The universe was not a static stage on which cosmic actors played their parts. It was the play itself, an unfolding dynamic and growing entity. Imagine a loaf of raisin bread rising in an oven. As the dough expands, every raisin moves away from every other raisin. From the perspective of any single raisin, it would appear that all the others are rushing away from it, and the ones farthest away would appear to be moving the fastest. This is the universe we inhabit. The galaxies are the raisins, and we are simply one of them embedded within a swelling space-time that carries everything along for the ride. This grand orderly expansion became known as the Hubble Flow, a majestic, uniform cosmic river carrying all of creation with it. It was a picture of elegant simplicity. The universe had a clear, overarching rule, a fundamental motion that governed everything on the largest of scales. Our place in this cosmic river seemed straightforward. We were simply adrift on its currents, our motion dictated by the primordial expansion that began with the Big Bang. For a time, this beautiful, orderly model seemed complete. It answered the biggest questions about the nature of the cosmos. But science thrives on testing its most elegant theories, on searching for the subtle cracks in a perfect facade. And as our ability to measure the universe grew more precise, a deep and unsettling anomaly began to emerge. The problem was hidden not in the distant galaxies, but right here in our own cosmic backyard. The Hubble flow described the universe on its grandest scale, but on smaller local scales another force was at play: gravity. Gravity is the great sculptor of the cosmos. While the expansion of space pushes everything apart, gravity pulls everything together. It binds stars into galaxies, galaxies into clusters, and clusters into gargantuan superclusters. These two forces are in a constant epic tug of war. In our local neighbourhood where matter is densely packed, gravity wins. The Andromeda Galaxy, our closest major neighbour, is not receding from us. Instead, it is hurtling toward us at 250,000 miles per hour, drawn by the irresistible pull of our mutual gravity, destined for a titanic collision billions of years in the future. This motion separate from the overall Hubble flow is what astronomers call a peculiar velocity. It is the personal localized motion of a galaxy, a deviation from the smooth cosmic expansion caused by the gravitational nudges of its neighbours. Think of the Hubble flow as a vast wide river moving steadily toward the sea. Most boats on this river simply drift with the current, but some boats have engines. They can move sideways or even struggle upstream for a short distance. Their motion is a combination of the river's flow and their own peculiar engine-driven movement. Every galaxy has a peculiar velocity, a small gravitational signature of its local environment. For decades, we assumed our own galaxy's peculiar velocity was relatively minor, a gentle drift caused by the pull of Andromeda and other nearby members of our local group of galaxies. There was no reason to think otherwise, but to truly know our own motion, we needed a fixed absolute reference point, a cosmic lighthouse, against which we could measure our true speed and direction. For a long time we didn't have one. The universe, it seemed, had no ultimate "you are here" sign. And then in 1964 we found it. Two American radio astronomers, Arno Penzias and Robert Wilson, were trying to eliminate a persistent faint hiss from a large radio antenna in New Jersey. This noise was everywhere. They pointed the antenna a constant low-level hum coming from every direction in the sky. It was uniform, unchanging day and night, season after season. What they had accidentally stumbled upon was the most ancient light in the universe. It was the afterglow of the Big Bang itself. This is the cosmic microwave background, or CMB, a faint primordial radiation that fills all of space, left over from a time when the universe was a hot, dense fireball. This light, which has been travelling for 13.8 billion years, provides the ultimate cosmic backdrop, a snapshot of the infant universe. And because it comes to us from every direction, it creates a universal frame of reference. It is the one thing in the universe that can be considered truly at rest with respect to the Hubble flow. Against this static backdrop, we could finally definitively measure our own peculiar velocity. Satellites were launched, instruments of incredible sensitivity were built, all designed to map this ancient light with exquisite precision. And when the data came in, it delivered a shock. The cosmic microwave background was not perfectly uniform from our perspective. In one direction of the sky, the light was slightly warmer, its wavelengths compressed, it was blue shifted. In the opposite direction, the light was slightly cooler, its wavelengths stretched, it was red shifted. The interpretation was inescapable. We were not gentle drifters on the cosmic river. We were a speedboat rocketing through the universe at a truly astonishing speed. After subtracting the motion of the Earth around the Sun and the Sun around the galaxy, the results showed that our Milky Way, along with our entire local group of galaxies, is careening through space at 1.3 million miles per hour. That's over 600 kilometers every single second. The speed was breathtaking, but it was the direction that created the mystery. We were heading toward the constellation Centaurus, a direction far away from any obvious massive object we could see. The simple gravitational tug of our known neighbours like Andromeda's was nowhere near powerful enough to explain this motion. It was like seeing a small boat being dragged across a lake at high speed by an invisible rope. Something huge, something unseen had to be pulling us. The hunt was on for the source of this colossal gravitational pull. The astronomical community was galvanised. Teams around the world began mapping the distribution of galaxies in every direction, searching for a massive concentration of matter, a cosmic heavyweight responsible for our incredible velocity. The task was immensely challenging. Much of the sky in the direction of our motion is obscured from our view. This region, known as the zone of obscuration, is where the plane of our own Milky Way galaxy lies. Our view is blocked by a thick screen of dust gas, and the light of billions of our own local stars, making it incredibly difficult to see the distant galaxies that lie beyond. It was like trying to spot a mountain range through a dense fog. But astronomers are clever. They used radio telescopes which can peer through the dust and infrared surveys which can detect the heat signatures of hidden galaxies. Slowly, painstakingly, a new map of our local universe began to take shape. And in the 1980s, a team of astronomers who dubbed themselves the Seven Samurai began to see the outlines of something truly monstrous lurking behind the veil of the Milky Way. It was not just a cluster of galaxies, but a supercluster, a sprawling city of galaxies hundreds of times more massive than our own, a gravitational behemoth containing the mass of a quadrillion suns. They called it the Great Attractor. Here, it seemed, was the answer. This was the unseen anchor, the gravitational monster that was reeling us in. Its immense mass, concentrated some 150 to 250 million light-years away, was exerting an inexorable pull on everything for hundreds of millions of light-years around it, including our own Milky Way. It was a satisfying solution. The universe once again made a certain kind of sense. Our peculiar velocity was no longer peculiar. It was the result of falling toward the largest gravitational well in our neighborhood. The mystery seemed solved. For a time, the Great Attractor was the accepted explanation, the final word on our cosmic trajectory. But the best scientists are never truly satisfied. They continued to refine their measurements, to sharpen their maps of the cosmos, to calculate and recalculate the mass of the Great Attractor and the strength of its pull. And as the data grew more precise, a familiar feeling began to creep back into the field. Doubt, a nagging discrepancy, a ghost in the machine. The numbers just weren't adding up. When astronomers carefully calculated the total gravitational pull exerted by all the visible matter in the Great Attractor, they arrived at a stunning conclusion. It was nowhere near enough. The Great Attractor was indeed massive, a formidable cosmic structure. Its pull on us was undeniable, a significant part of our journey, but it could only account for at most about half of our measured velocity. The invisible rope pulling our galaxy was far stronger than the object we thought was holding it. We had found the culprit only to realize it couldn't have committed the crime on its own. It had to have an accomplice. This was the dawn of a profound new conundrum. The greatest known concentration of mass in our vicinity was insufficient to explain our motion. The equation of our cosmic journey was unbalanced. Something else was missing from the picture, another massive gravitational influence that had to be out there shaping our path, pulling us forward. For years, the search focused on finding an even greater attractor, a greatest attractor, lurking even deeper in space, perhaps beyond the first one. And indeed, subsequent surveys did find larger structures like the Shapley Supercluster, located far behind the Great Attractor. But even when the pull of this and other distant structures was added to the equation, the math still fell short. Our speed was still too high, our direction was still not fully explained. The pull from behind this cosmic siren song drawing us forward was only part of the story. The answer wasn't adding up because we were only looking at one side of the equation. We were obsessed with what was pulling us. We were consumed by the search for mass, for density, for attraction. It never occurred to us to turn around, to look in the opposite direction, to consider that perhaps the greatest force shaping our destiny was not a pull from the front, but a push from behind. A push coming from a place we had always dismissed as insignificant. A push from the empty, silent and forgotten voids of the universe. And so the mystery remained a cosmic current pulling us toward an unseen shore. But to solve the riddle of where we're going, we first had to answer an even more fundamental question. Where precisely are we? For centuries, our maps of the universe were flat, two-dimensional projections of the night sky. Beautiful, but profoundly misleading. We saw the stars and galaxies as jewels sewn onto a black velvet curtain, their true distances from us a matter of educated guesswork, their relationships to each other a complete enigma. To comprehend the force acting upon our Milky Way, we needed to pull back that curtain. We needed to chart the universe in 3 dimensions to replace the celestial sphere with a true cosmic atlas. A new era of cartography was dawning, one that would not map continents or oceans, but the very architecture of creation itself. The key to this revolution was not a new kind of telescope, but a new way of listening to the light. Every galaxy sings a song, a spectrum of light, encoded with the chemical secrets of its stars. But this light, as it traverses the expanding fabric of space-time, becomes stretched, its wavelength elongated, its pitch shifted toward the red end of the spectrum. This is redshift, the universe's own Doppler effect. It's more than just a colour change. It is a cosmic clock, a measure of distance. The greater the redshift, the faster a galaxy is receding from us, and thanks to the laws of cosmic expansion, the farther away it must be. Suddenly astronomers had their third dimension. They had a yardstick that could span the cosmos. The monumental task fell to a new generation of pioneers astronomers who weren't just content to photograph beautiful nebulae. They were surveyors, cosmic geographers armed with spectrographs and boundless patience. At observatories across the globe, teams like the one led by Margaret Geller and John Huchra at the Harvard Smithsonian Center for Astrophysics began a grueling campaign. Night after agonizing night, they would point their telescopes at one faint, fuzzy patch of light, then another and another. For each one, they would painstakingly capture its spectrum, a faint rainbow of light smeared across a detector. From that smear, they would calculate a single number, its redshift. It was slow, meticulous, almost thankless work. Each data point, each galaxy placed on the map was the culmination of hours of observation and analysis. They were mapping the universe one photon at a time, building a picture of our cosmic neighbourhood, not with broad brushstrokes, but with the painstaking precision of a pointillist painter. In the early days, their map was sparse, a few lonely points floating in a black digital void. It was impossible to see any pattern. But as the months turned into years and the catalogue of galaxies grew from a few hundred to a few thousand, something extraordinary and completely unexpected began to emerge from the darkness. The points were not scattered randomly like dust motes in a sunbeam. They were connected. Before your very eyes, the universe was revealing its true form. It was not a uniform sea of galaxies, but a vast interconnected structure of unbelievable scale and complexity. We came to call it the cosmic web. It was a structure of breathtaking beauty and startling emptiness. Long, luminous tendrils of galaxies, some stretching for hundreds of millions of light years, snaked through the void, forming majestic filaments. These were the great rivers of the cosmos, flowing with stellar light, their banks defined by the gentle, persistent pull of gravity. Where these filaments intersected, they gave rise to dense, dazzling knots of matter, the great clusters and superclusters. These are the sprawling metropolises of the universe, cosmic cities, ablaze with the light of 1,000 galaxies locked in a chaotic gravitational dance. Entire walls of galaxies, vast flattened sheets of matter, partitioned the cosmos, forming the boundaries of immense cavernous regions. And between it all, nothing, or more accurately, next to nothing. The surveys revealed voids, colossal bubbles of emptiness dwarfing everything else in the cosmic inventory. These were not mere gaps. They were monstrous caverns of space-time so vast that our entire local group of galaxies would be but a speck of dust lost within one. The discovery was a paradigm shift. The universe we thought we knew, a relatively homogeneous space, was a fiction. The reality was a delicate frothy structure like cosmic sea foam, where almost all the matter we can see is concentrated into less than 10% of the volume. The rest is the deep, dark, silent ocean of the void. Our perception of the cosmos was forever altered. We were not adrift in a random starfield. We lived within a celestial lacework of unimaginable intricacy. This new map was a triumph, but it was still a static picture. It showed us where things were, but not how they were moving. And the original mystery remained unsolved: what was pulling the Milky Way. The redshift that allowed astronomers to build this map was dominated by the overall expansion of the universe, the Hubble flow. It was like trying to hear a whisper in a hurricane. Every galaxy is rushing away from every other galaxy as space itself expands. But that's not the whole story. Gravity is still at work. That incredible cosmic web with its dense clusters and massive filaments exerts its own influence. It creates local gravitational currents, subtle eddies, in the great outflow of cosmic expansion. A galaxy isn't just carried along by the expansion, it is also falling toward the nearest massive structure, be it a neighbouring galaxy, a cluster, or a filament. This extra motion separate from the Hubble flow is what we call a galaxy's peculiar velocity. And measuring it is one of the most difficult tasks in observational astronomy. To find it, you have to know a galaxy's true distance with incredible precision, independent of its redshift. Then you can compare its redshift implied velocity with the velocity it should have at that distance. The difference between the two, that tiny residual speed, is the peculiar velocity. It's the galaxy's own motion through its local cosmic environment. It is the signature of gravity at work. Astronomers needed a new set of tools, clever methods for measuring cosmic distances that didn't rely on redshift. They found them in the galaxies themselves. For spiral galaxies, they used a discovery known as the Tully-Fisher relation, a remarkable correlation between how fast a galaxy spins and its intrinsic brightness. By measuring its rotation speed, you can deduce its true luminosity. By comparing that to how bright it appears in our sky, you can calculate its distance with astonishing accuracy. For other types of galaxies, they hunted for standard candles, astronomical objects with a known predictable brightness. Certain types of stellar explosions, type Ia supernovae, became the gold standard. These cosmic beacons flare up with a consistent brilliant luminosity, allowing astronomers to use them as distance markers across billions of light years. Armed with these techniques, teams of researchers began a new, even more ambitious survey. They weren't just mapping positions anymore, they were mapping motion. For thousands of galaxies in our cosmic vicinity, they measured these peculiar velocities. They were adding arrows to the dots on their map, revealing the hidden currents of the cosmic river. The work was fraught with uncertainty. Each measurement carried large error bars. It was like trying to clock the speed of a firefly from miles away on a foggy night. But slowly, painstakingly, a coherent picture of our local flow field began to take shape. And it was deeply strange. As the data accumulated, a startling pattern became undeniable. Galaxies in our corner of the universe were not moving randomly. They weren't all being drawn toward a single predictable point of immense mass, like water spiraling down a drain. Instead, the astronomers saw a large-scale organized bulk flow. Thousands of galaxies, including our own Milky Way and our neighbors in the local group, were all streaming in roughly the same direction, a coherent motion that couldn't be explained by the visible structures alone. The Great Attractor, that dense supercluster region, accounted for some of this motion, but not all of it. There was still a significant component of our velocity left over, an anomaly that pointed somewhere else. But the most bizarre part of the pattern was not just where galaxies were going, but where they were coming from. When astronomers traced the velocity vectors backward, they noticed something profound. The flow seemed to be diverging, moving away from a particular unusually empty patch of the sky in the southern celestial hemisphere. It was as if our entire cosmic neighborhood was on the downslope of a vast gravitational hill. The maps confirmed it. The new three-dimensional surveys, which were becoming more detailed with each passing year, showed a significant deficit of galaxies in precisely that direction. There was a hole in the universe right next door, a region far less dense than the cosmic average. This was the first concrete observational evidence, the first inkling of a radical new idea. The astronomer R. Brent Tully, at the University of Hawaii, was among the first to connect the dots to put the two extraordinary datasets together, the map showing an absence of matter and the velocity measurements showing a flow away from that same absence. The implication was as counterintuitive as it was profound. What if the primary force driving our galaxy's peculiar motion wasn't a pull, but a push? Not an attraction towards something massive, but a repulsion from something empty. This was a concept that seemed to defy common sense. Gravity, as we know it, only pulls. It is the force of attraction between masses. How could a lack of mass and emptiness exert any force at all? The answer lies in the cosmic context. On the grandest scales, gravity is a game of tug-of-war. Every galaxy is being pulled in all directions by the surrounding matter in the cosmic web. If the universe were perfectly uniform, all those pulls would cancel each other out, and the galaxy would only experience the outward rush of cosmic expansion. But our universe is not uniform. Imagine you're floating on a perfectly still lake. Now imagine a vast volume of water is suddenly removed from the lake to your left. You won't feel a push from the empty space. Instead, the pressure and pull from the water on your right, now unopposed by the water that is no longer there, will gently but inexorably move you away from the void. This is the nature of the cosmic push, the local void. This vast underdense region isn't actively shoving us. It is creating a gravitational deficit. The gravitational pull from the structures on the opposite side of the sky, like the Shapley Supercluster, is now more effective, less counteracted. We are not being pushed from behind so much as we are being pulled forward with less resistance from the empty region we are leaving in our wake. The void creates a gradient in the gravitational field, and our local group is simply rolling downhill away from it. This hypothesis was elegant, but for many in the astronomical community it was a step too far. It was one thing to identify voids as a structural component of the universe. It was another thing entirely to claim that one of them was an active gravitational player, the dominant engine of our galaxy's motion. Skepticism, the lifeblood of good science, ran deep. The challenges were immense and the objections were powerful and legitimate. How could we be sure the void was real? The process of counting galaxies is notoriously difficult. Our own Milky Way is filled with gas and dust that obscures our view of distant objects, particularly in the plane of the galaxy itself. Could this zone of avoidance be fooling us? Perhaps the void wasn't a true absence of galaxies, but merely a region where they were hidden from our view, their light blocked by galactic smog. This was a serious concern, and astronomers had to develop complex models to correct for this obscuration, a process that introduced its own uncertainties. Even if the deficit of galaxies was real, was it statistically significant? The distribution of galaxies is lumpy. Finding an underdense region could simply be a fluke, a chance arrangement that held no deeper meaning. Proving that the local void was emptier than cosmic chance would allow required far more data than the early surveys provided. Furthermore, the peculiar velocity measurements themselves were under intense scrutiny. These were and still are fantastically difficult observations to make. The uncertainties in the distance measurements were large, which meant the calculated velocities could have significant errors. Critics argued that the coherent bulk flow could be an illusion, a systematic error in the data masquerading as a real cosmic current. Perhaps the standard candles weren't as standard as we thought. Perhaps our understanding of the Tully-Fisher relation was incomplete. Every link in the observational chain was questioned, every assumption challenged. The idea of a void acting as a cosmic repeller felt like a ghost story to many researchers. It was an explanation based on an absence of force defined by what wasn't there. Science prefers to deal with tangible objects with measurable masses and observable energies. To attribute the motion of our galaxy to a vast emptiness seemed like invoking a phantom. The burden of proof was enormous. To convince the world, the proponents of this theory needed more than just a tantalizing correlation. They needed a map so detailed it would leave no doubt about the void's existence and scale. They needed velocity measurements so precise they would silence the critics. They had found a whisper in the cosmic static, a hint of a colossal invisible hand shaping our destiny. But for now, it was just that, a hint. The local void was a ghost in the machine, a compelling but unproven theory haunting the fringes of our cosmic charts, waiting for the light of further discovery to either banish it as a phantom or reveal it as a fundamental truth of our existence. And so the equation remained stubbornly, infuriatingly unbalanced. The great cosmic ledgers, meticulously kept by generations of astronomers, simply refused to add up. We had accounted for the colossal pull of the Virgo cluster, factored in the relentless tug of the Norma cluster inside the Great Attractor, and even calculated the immense gravitational summons of the distant Shapley Supercluster, that sprawling continent of galaxies lying far beyond. Collectively, they were the great engines of our cosmic motion, the titans of gravity whose existence was written in the orbital dance of every galaxy in our neighbourhood. They pulled, and we moved. It was the elegant, undeniable logic of a universe governed by mass. Yet when we measured our true velocity, that bewildering 630 km per second rush, relative to the afterglow of the Big Bang, a discrepancy persisted, a phantom velocity. A significant portion of our motion through the cosmos, an entire vector of movement, remained utterly unexplained. It was as if we were a ship being drawn forward by visible currents, while also being pushed by an invisible tide from behind. This was more than a rounding error. It was a fundamental challenge to our understanding. Cosmology. A science built on the precise accounting of forces had a ghost in its machine. The pull we could see was not strong enough. Something else, something unseen and unaccounted for, was contributing to our cosmic journey. For decades, this anomaly festered at the heart of our cosmic map, a constant reminder that the chart was incomplete, that some great feature of our local universe was missing entirely. The search for more mass for another, even greater Great Attractor hidden behind the veil of the Milky Way yielded nothing. Telescopes stared into the void and found only that void. The intellectual impasse forced a profound and deeply counterintuitive shift in perspective. It was a thought so contrary to the fundamentals of cosmic mechanics that it was almost heretical. What if we had been looking in the wrong direction all along? What if the answer wasn't about finding more pull in front of us, but in acknowledging a profound lack of it behind us? What if the missing piece of the puzzle wasn't a presence but an absence? This was a revolutionary, almost paradoxical idea. Gravity, as we understand it, is a force of attraction. It summons, it gathers, it pulls. It does not push. The concept of a repulsive force on these scales belonged to the realm of exotic physics of dark energy, driving the universe's expansion on the grandest of stages, not to the local traffic of galaxies. How could emptiness, the very definition of nothing, exert any influence at all? The answer required a new kind of map. Not a map of where galaxies are, but a map that could faithfully represent where they are not. This was the monumental task undertaken by international teams of astronomers, led by pioneers like Brent Tully at the University of Hawaii and Hélène Courtois at the University of Lyon. They embarked on a project of staggering ambition to create the most comprehensive three-dimensional atlas of our corner of the universe. It was called Cosmic Flows. The goal was not just to chart the position of galaxies, but to measure their peculiar velocities, their individual motions separate from the overall expansion of the universe. Each galaxy's unique movement is a fingerprint left by the local gravitational field. A galaxy being pulled toward a supercluster will show a slight blue shift, a velocity component aimed at the mass. A galaxy on the far side of that same supercluster will be pulled back, showing an additional redshift. These subtle deviations from the smooth cosmic expansion are the key. They are the whispers and echoes of gravity at work. By measuring the motions of thousands upon thousands of galaxies, you can reverse engineer the landscape that creates those motions. You can infer the location of the great mountains of mass, the cosmic superclusters, without ever seeing them directly. You can trace the gravitational valleys and riverbeds that guide the flow of galaxies across the eons. It was painstaking, meticulous work spanning years and involving observatories across the globe. Each data point was a single galaxy. Its light captured its spectrum, analysed its distance, and velocity calculated with painstaking precision. As the data points accumulated, a picture began to form. Slowly, dot by dot, the cosmic web in our vicinity was illuminated. As expected, the great structures appeared. The Virgo cluster, the Perseus-Pisces supercluster, the distant Shapley concentration, they all resolved into view as regions where the peculiar velocities of galaxies all converged like rivers flowing into a great sea. The map was confirming what we already knew. But then, as the cartographers surveyed the region directly behind us in the opposite direction of our overall motion, a stunning feature began to take shape. Or rather, a lack of one. It was a void. An area of space so breathtakingly profoundly empty it defied all statistical expectations. This wasn't just a quiet patch of sky, it was a chasm. A region hundreds of millions of light years across where the density of matter dropped to a fraction of the cosmic average. Where there should have been thousands of galaxies, there were but a handful of lonely stragglers. It was as if we were living on the coast of a vast dark ocean of nothingness. This was the definitive identification of the feature we now call the local void. The data from the Cosmic Flows project and others like it provided the irrefutable evidence. It was real, it was immense, and it was right next door. Our own local group of galaxies containing the Milky Way and Andromeda sits on the very edge of this colossal underdensity. We are perched on the shore of a cosmic desert. To fully grasp the scale of this structure is a challenge for the human mind. If our Milky Way galaxy were a single grain of sand, the local void would be a chasm stretching for miles. It is a place where the vibrant tapestry of the cosmic web has frayed and torn, leaving behind a barren expanse. For billions of years, this region has been bleeding matter, its sparse contents siphoned off by the gravitational might of the denser regions surrounding it, leaving it ever more empty, ever more desolate. This is not the active energetic vacuum of deep space between stars or planets. This is a structural void, a fundamental emptiness woven into the very fabric of the cosmos. The confirmation of its existence was a landmark achievement, a new continent added to our celestial maps. But its discovery did more than just fill in a blank space. It provided the final crucial key to unlocking the mystery of our own motion. The puzzle pieces suddenly snapped into place with breathtaking clarity. Imagine yourself floating in the exact center of a swimming pool. If swimmers all around you are splashing, creating waves that push you from every direction, the net force is zero. You remain more or less in the middle. The pushes from all sides cancel each other out. Now imagine that all the swimmers on one side of the pool suddenly climb out. There is no one behind you to create a new magical pushing force. Instead, there is simply the absence of the pushes that were once there. The waves from the swimmers still in front of you are no longer counteracted. The result: you accelerate away from the empty side of the pool, pushed forward by the remaining now unbalanced forces. The emptiness itself does not push. The emptiness allows you to be pushed. This is the principle that governs our galaxy's motion. The universe is filled with the gravitational splashing of superclusters pulling on us from all directions. For eons, the pull from the structures in front of us, Virgo the Great Attractor Shapley, was counterbalanced at least in part by the pull from whatever matter lay behind us. But the local void is the empty side of the pool. It is a profound gravitational deficit. The lack of mass in that direction, the absence of a gravitational anchor pulling us backward, means the pull from the concentrations in front of us is now unopposed. Our galaxy is not so much being pushed from behind as it is being let go from behind, allowing the forward pull to become far more effective. It's a cosmic undertow, an inexorable slide down a gravitational gradient away from the shallows of the void and towards the deep gravity wells of the superclusters. This concept, elegant and powerful, was given a name by the research team of Yehuda Hoffman, Daniel Pomered, Brent Tully, and Hélène Courtois. They called it the dipole repeller. The name is poetic yet precise. Our motion has a dipole nature. We are moving from one point to another, and a significant component of that motion is caused by the effective repulsion from this vast void. The local void acts as our dipole repeller. It is the ghost in the machine finally given a face. The push from this newly identified void, when combined with the pull from the known superclusters at last, made the cosmic ledger balance. The phantom velocity was vanquished. The unexplained component of our 630 km/s rush was accounted for. The calculations for the first time matched our observations of the cosmic microwave background perfectly. It was a moment of profound revelation, a collective sigh of relief for a generation of cosmologists. The solution was not a single gargantuan object, but a delicate and vast environmental effect. Our motion is a cosmic dance choreographed by both the seen and the unseen, a story written not just by the great cities of light, the superclusters, but by the enormous silent deserts of darkness that lie between them. The discovery of the local void and the dipole repeller fundamentally changed our place in the universe. We are not merely island inhabitants being swept along by a single powerful current. We are coastal dwellers living on the shore between a continent of matter and an ocean of nothing. Our journey through space is the net result of this grand cosmic topography, pushed from the empty quarter behind us and pulled toward the great massifs that lie ahead. It is a picture of sublime complexity and astonishing elegance, where the largest and most empty features of the universe exert as much influence on our destiny as the largest and most dense. We finally understood the why of our local motion, the complete set of forces that have charted our galaxy's path through space and time for billions of years. But in solving one mystery, we had uncovered a deeper one. This void, this gargantuan bubble of cosmic emptiness, could not have been there from the beginning. It had to have been sculpted, carved out of the primordial universe by the unyielding forces of gravity and the enigmatic presence of dark matter. Its very existence is a testament to the colossal battle between cosmic expansion and gravitational collapse that has shaped everything we see. To understand the local void, therefore, is to seek the origin story of the cosmic web itself. We must now journey back in time, back to an era when the universe was smooth, hot and dense, to find the tiny quantum seeds from which these great deserts and the glittering filaments that surround them first grew. And so we are confronted with a question that seems to defy logic, a paradox that cuts to the very heart of how we perceive the universe. How can nothingness exert a force? How can an absence of matter, a desolate expanse of cold, dark emptiness, propel our Milky Way and its neighbours at 1,000,000 miles an hour? The answer requires a profound recalibration of our intuition, a shift in perspective from seeing gravity as a simple pull to understanding it as the complex dynamic architecture of space-time itself. The local void doesn't push us with some mysterious exotic energy. There is no anti-gravity at play here, no strange new physics. The force it exerts is still gravity, the same ancient familiar force that holds you to your chair and binds the Earth to the Sun. But it is gravity acting in reverse, not through attraction, but through a conspicuous and consequential absence of it. Imagine you're on a vast calm lake in a small boat, and from every direction immensely strong, ropes are tied to your vessel, pulling on it, with equal tension from all points of the compass. You would be held perfectly in place, a captive of cosmic equilibrium balanced by the gravitational pull of all the mass in the universe around you. Now imagine that on one side a colossal pair of shears severs all the ropes. Suddenly the balance is broken. You're not pushed from the side where the ropes were cut. Rather, you are now pulled unimpeded by the ropes on the opposite side. Your motion is a direct consequence of the void that was created behind you. This is the secret of the local void's power. It isn't a hand at our back shoving us forward. It is a profound gravitational deficit, a cosmic anchor that has been lifted. For billions of years, the matter that once might have occupied this region has been draining away, siphoned off by the irresistible pull of the denser structures forming along its periphery. As it emptied, its gravitational influence on us dwindled to almost nothing. Meanwhile, on the other side of our cosmic neighbourhood, the immense gravitational anchors of the Virgo Supercluster, the Hydra Centaurus Supercluster, and the even more distant behemoth structure known as the Shapley concentration never let go. Their pull on us, once counterbalanced by the mass in the void's direction, is now the dominant force shaping our trajectory. We are not so much being pushed from behind as we are being drawn forward into the arms of the greatest galactic empires in our corner of the cosmos, our journey accelerated because the gravitational terrain behind us has fallen away. Think of it as a cosmic watershed. The local void is a vast elevated plateau of space-time, a negative mountain. Not a mountain of mass, but a mountain of absence. And from this high ground of cosmic emptiness, galaxies like ours flow away like rivers seeking lower ground. We are caught in a gravitational current, a celestial slipstream, and the source of this current, the headwaters of our cosmic river, is the centre of this immense vacuity. It is a relentless, gentle, and inescapable pressure, the cumulative effect of being pulled by everything in one direction and virtually nothing in the other. This understanding transforms our view of the universe's grand design. For decades, astronomers pictured the cosmos as a web of glowing filaments, luminous threads of galaxies and dark matter stretching across the darkness. The voids were merely the gaps in between the leftover dark spaces. But this perspective is fundamentally flawed. It's like describing a sponge by focusing only on the rubber and ignoring the holes that give it its structure. The voids are not the absence of structure. They are the structure. They are the colossal expanding bubbles in the cosmic foam, and the glittering superclusters we see are merely the luminous froth where these immense bubbles press against one another. These voids dominate the universe by volume, making up more than 80% of the observable cosmos. The grand filaments of the cosmic web, those shining rivers of galaxies, are not the primary feature of the universe. They are the boundaries, the thin glowing membranes that delineate the true empires of the cosmos, the silent, dark, and astonishingly empty kingdoms of the great voids. Our universe is a universe of voids, and we are simply living on the shore of one. To comprehend the sheer scale of this dominion, we must journey back in time, back to the universe's very first moments, a fraction of a second after the Big Bang. The cosmos then was an almost perfectly smooth, searingly hot soup of energy and particles, almost but not quite. Imprinted upon this primordial plasma were infinitesimal quantum fluctuations, minuscule variations in density, like near imperceptible ripples on a flawless pond. Some regions were by sheer chance infinitesimally denser than average, while others were infinitesimally less dense. As the universe expanded and cooled, gravity began to act upon these tiny seeds. It was a story of the rich getting richer and the poor getting poorer played out on a cosmic scale. The regions that started with a tiny bit more mass began to pull in matter from their surroundings. Their gravitational advantage, however slight, compounded over millions, then billions of years. Matter flowed towards them, draining from the neighbouring regions, accreting into the first halos of dark matter, which in turn attracted gas-ignited stars and forged the galaxies and clusters we see today. These overdense regions became the great gravitational basins of the universe, the destinations for all inflowing cosmic material. They are the luminous filaments, the bustling galactic cities. But what of the regions that started with slightly less matter? They became the voids. Their story is not one of passive emptiness, but of an active hollowing out process. As their denser neighbours grew more massive, their gravitational pull became ever more powerful, stripping away what little matter these underdense regions possessed. Like cosmic deserts, they were starved of the material needed to form galaxies. While the rest of the universe was furiously building stars and structures, these areas were being systematically emptied, their contents evacuated. And as the universe expanded, a process driven by dark energy, these underdense regions expanded faster and more dramatically than the dense ones. Gravity was fighting against expansion in the filaments, trying to hold things together, but in the voids there was almost nothing to resist the cosmic stretch. They swelled to gargantuan proportions, becoming vast spherical deserts of space-time. The local void is one such desert, a relic of an initial quantum seed of underdensity that has been growing and emptying for 13.8 billion years. It is not merely empty space, it is an echo of creation's first imperfections, a ghost of the mass that was never there to begin with, and a testament to the relentless power of gravity to sort the universe into kingdoms of light and shadow. What makes our local void so profoundly important to us, distinguishing it from the countless other voids scattered across the cosmos, is a simple, terrifying matter of geography. Its sheer size is staggering, a chasm nearly 200 million light-years across. You could fit thousands of Milky Way galaxies inside it with room to spare, but it is its proximity that makes it a dominant force in our destiny. We are not observing this void from a safe distance. We are living on its very edge, our galactic suburbs bordering this immense wilderness. The centre of the void is only about 100 million light-years away, a stone's throw in cosmic terms. This means its gravitational influence or lack thereof is not a subtle distant effect. It is the primary engine behind our local cosmic flow. It is the invisible hand that has shaped the architecture of our galactic neighbourhood, defining the very currents of space-time in which our galaxy swims. For so long we believed our motion through space was solely dictated by attraction. We saw the pull of the Virgo cluster, the core of our home supercluster, and we understood we were falling toward it. Then we discovered the Great Attractor, a much larger gravitational anomaly hidden behind the plane of the Milky Way, and later the Shapley Supercluster, the largest concentration of galaxies in our local universe. Our cosmic story seemed to be one of falling, of being inexorably drawn towards ever greater mountains of mass. The local void fundamentally rewrites that story. It reveals that our journey is not just a fall, but also a flight. It's a push just as much as it is a pull. Cosmologists calculate that this void repulsion accounts for at least half of our galaxy's peculiar velocity, the speed and direction of our motion that is not due to the overall expansion of the universe. Half of our journey through the cosmos is dictated not by what lies ahead, but by the great gaping emptiness that looms behind. This creates a magnificent and dramatic tension, a cosmic tug-of-war with our Milky Way caught squarely in the middle. In one direction lies the void, a gravitational desert pushing us away, its influence subtle but expansive, like a steady, powerful wind at our backs. In the other direction, the superclusters of Virgo, Hydra, Centaurus, and Shapley beckon to us their combined gravity, a focused, powerful summons from across the universe. We are trapped in the middle of a cosmic contest between absence and presence, between the gravitational call of the most crowded places in the universe and the gravitational silence of one of its most desolate. This dynamic interplay is not just an academic curiosity. It is the lived reality of our galaxy's existence. It explains the structure we see around us, the so-called local sheet of galaxies, of which we are a part, a flattened collection of galaxies, including our own local group that appears to be flowing away from the void, like debris on the surface of an expanding bubble. It orients our place in the cosmos, giving us a new and profound understanding of our cosmic address. We live on the far side of the Laniakea Supercluster, on the very precipice of a colossal abyss. The local void is the missing piece of the puzzle of our motion, the unseen puppeteer that, alongside the Great Attractors, pulls the strings of our galactic destiny. It forces us to accept that the most significant features of the universe are not necessarily the ones that shine the brightest. Sometimes the most powerful and formative structures, the ones that truly define our place in the cosmos, are the ones that are defined by an overwhelming, profound and magnificent nothing. We have established the physics, the sheer mind-bending reality of how this empire of emptiness can steer the fates of galaxies. We understand its origins in the faint whispers of the Big Bang and its role as the dominant feature of our cosmic geography. But this raises an even more challenging question. How do you map a ghost? How do you survey the boundaries of something that is defined by its absence? To chart the contours of the local void required astronomers to become celestial cartographers of the invisible, to find ingenious new ways to see what isn't there, and in doing so to unveil the true hidden architecture of our universe. The story of that exploration, a detective story written in the faint light of distant galaxies, is where our journey must now turn. And so we stand at a cosmic crossroads holding the pieces of a puzzle vast beyond comprehension. We have traced the gravitational tethers pulling our Milky Way forward, feeling the insistent tug of the Virgo cluster, the deeper summons of the Centaurus and Norma clusters, and beyond them all the almost mythical allure of the Shapley Supercluster, that great concentration of mass toward which everything in our vicinity seems to be flowing. Each is a powerful cosmic engine, a vortex of gravity reeling us in over the eons. Yet when we sum their forces, when we meticulously calculate the combined pull on our local group, a profound discrepancy remains. The math does not resolve. Our observed velocity, the incredible speed at which we are hurtling through the universe, is still too high. The direction is subtly, but undeniably wrong. It's as if an unseen hand were on our back, a silent, persistent pressure, adding its own momentum to the grand equation of our cosmic motion. For decades, this anomaly haunted the edges of our cosmological maps, a ghost in the machine of galactic dynamics. We were being pulled, yes, but we were also being pushed. To truly understand our journey, to plot the true course of our galactic destiny, we could no longer ignore the immense silent emptiness we are leaving in our wake. We had to turn around and finally confront the void, to witness this cosmic ballet in its entirety, to see the push and the pull acting in concert. No single telescope is powerful enough. No human lifetime is long enough to observe the motion. We need a time machine and a God's eye view, a way to compress billions of years into seconds, and to see the architecture of the universe from the outside looking in. This is a power we now possess not in reality, but in the digital heart of our most advanced supercomputers. Here we can build a new cosmos from scratch. We feed the machine everything we know, the precise afterglow of the Big Bang, the cosmic microwave background radiation which holds the seeds of all structure. We input the locations of hundreds of thousands of galaxies, the measured masses of colossal clusters, the delicate filaments of the cosmic web, and the known laws of physics. Most importantly, Einstein's theory of general relativity. We create a digital twin of our universe, a multi-petabyte sandbox where gravity is the only rule. With a single command, we press play. We let loose the gravitational arrow of time and we watch. We watch as phantom matter coalesces along invisible scaffolds, as the first stars ignite in a silent pixelated fury, as galaxies spin into existence and begin their long, inexorable fall toward one another. In this virtual cosmos, we can isolate the forces, we can conduct the ultimate experiment. First, we run the simulation with only the pullers. We program our digital local group to feel only the gravitational attraction of Virgo Centaurus and the distant Shapley concentration. We watch its trajectory unfold over a simulated 14 billion years. The result is fascinating, a graceful arc through space-time. Our virtual home galaxy is indeed drawn out of its primordial slumber, accelerating towards these massive structures. It's a journey that looks plausible, one that captures the broad strokes of our cosmic story. But when we place this simulated path alongside the real observed trajectory of the Milky Way, the illusion shatters. The final vector is wrong. In the simulation, our galaxy's path hooks too sharply toward the known attractors. Our final velocity is too low. It's a close approximation, a beautiful failure that proves with mathematical certainty that we are missing a fundamental component of the story. The pull alone cannot explain our home's place in the universe. It cannot explain where we are, and it cannot explain why we are moving so fast. The model is incomplete. The ghost in the machine is still at large, its influence now more conspicuous than ever. So we reset the universe. We rewind time to the digital dawn. And this time we add a new variable. We input the void. We meticulously map the coordinates of that vast underdense region we call the local void, defining it, in the simulation, not by what it has, but by what it lacks. It isn't a source of anti-gravity. Such a thing doesn't exist. Instead, it is a region of profound gravitational absence. Imagine the fabric of space-time as a stretched membrane. A supercluster is a heavy weight, creating a deep depression, a gravity well into which everything nearby wants to fall. The local void in this analogy is the opposite. It's an area where the membrane has been lifted up a vast gentle hill on the cosmic landscape. It doesn't push in the conventional sense, it creates a slope. And we, the Milky Way, Andromeda, and all our small neighbours are rolling downhill away from it. This gravitational watershed, this subtle, large-scale, topographical feature of space-time is the missing piece of the puzzle. It is the cosmic negative pressure that cosmologists had long suspected but could never before model with such precision. It is the architect of the discrepancy. Now, with the void's influence programmed into the simulation, we run it again. We hold our breath as billions of years flash by in moments. The digital galaxies ignite, the clusters form, the great attractors begin their siren call, pulling our local group forward. But this time, something is different. From the opposite direction, from the vacant heart of the local void, a new dynamic emerges. Our galaxy and its neighbours feel the gravitational pull from the dense regions ahead of them, but they also feel the lack of pull from behind them. Every galaxy, every star, every atom in our local group is being pulled more strongly by the matter on the Shapley side of the universe than by the sparse, empty region on the void side. This imbalance, this relentless unidirectional deficit of gravity, acts exactly like a force. It is a gentle, unyielding pressure from behind. It is the universe's own hand pushing us forward. And as we watch the trajectory of our virtual Milky Way unfold this time, a sense of profound revelation descends. The path is no longer wrong. The graceful arc now perfectly matches our observed motion. The speed, the vector, the final destination, it all snaps into place with breathtaking accuracy. The ghost has been found. Its identity is certain. The local void is not a passive bystander in our story. It is one of the primary authors of our journey. This simulation allows us to finally dissect our motion to see the symphony of forces for what it is. We can visualize our velocity through space as a single arrow, and we can now see the smaller arrows that combine to create it. A significant portion of our speed comes directly from the pull of the Virgo cluster, our closest major gravitational anchor. Another vector points toward the Great Attractor region, a deeper and more powerful call. A smaller yet crucial component of our velocity is aimed at the far-off Shapley Supercluster, the ultimate destination on our multi-billion-year voyage. But when we add these vectors together, they only account for about half of our total speed. The other half, an enormous contribution to our momentum, is a vector pointing directly away from the geometric center of the local void. It is a repulsive velocity, a cosmic eviction notice served by emptiness itself. We are not just falling towards something, we are simultaneously fleeing from nothing. This dual nature is the central truth of our place in the universe. Our motion is a celestial compromise, a dynamic equilibrium between the gravitational abundance in front of us and the profound gravitational poverty behind us. It is a dance choreographed by mass in its absence. Think of our local group as a small boat on a cosmic ocean. Far ahead, several massive whirlpools, the superclusters, are pulling the water toward them, creating a powerful current. Our boat is caught in this current, drawn inexorably forward. This is the story we have always known. But what the simulations now show us is that behind our boat, the water level itself is higher. We are on the downslope of a colossal invisible wave. So not only is the current pulling us, but the very sea itself is flowing downhill, carrying us with it, dramatically increasing our speed. This is the influence of the local void. It is the slope on the ocean of space-time, a feature so large and so subtle that it took us a century of looking at the stars to finally perceive it. This understanding reframes our entire cosmic context. The local sheet, the flattened arrangement of galaxies that includes our own, is not just a random association. We can now see it as a coherent structure, its shape and motion dictated by this gravitational topography. It is a membrane stretched taut between the emptiness of the void and the density of the superclusters. It is the precise boundary of the watershed, the line where galaxies on one side begin to fall away from the void, and those on the other fall into some other basin of attraction. This grand, unified picture extends far beyond our own galactic neighbourhood. As we pan the camera out in our virtual universe, we see this is not a special case. It is a fundamental principle of cosmic structure. All around the perimeter of the local void, we witness the same effect. We see other small galaxy groups, our distant cousins in the cosmos, riding the same repulsive wave. They're all being shepherded away from the central emptiness, pushed out toward the luminous walls and filaments that define the void's boundaries. The local void acts like a cosmic sprinkler, spraying galaxies outward in all directions, toward the denser regions that encircle it. It is actively sculpting our corner of the universe, defining the frontiers of superclusters by feeding them a steady stream of galaxies. It is a kingmaker, its repulsive shadow helping to build the very empires of matter, whose gravity in turn helps to deepen the void's own emptiness. This is a feedback loop on an unimaginable scale, a cycle of cosmic construction and evacuation that has been running for billions of years. The void creates the superclusters, and the superclusters create the void. They are two sides of the same cosmic coin, locked in a perpetual creative tension. For us, this revelation is nothing short of transformative. It means the story of our home, the Milky Way, cannot be told without acknowledging this immense emptiness as a primary character. For our entire existence, humanity has looked up at the light at the brilliant stars and nebulae and seen our origins. We have defined ourselves by the matter we are made of and the celestial bodies we can see. But now we know that our destiny, our motion, our future trajectory is being shaped just as powerfully by the darkness, by the things that are not there. The local void is our silent, invisible partner in this cosmic dance. Its lack of substance provides the crucial counterbalance to the pull of everything else. It is the reason our galaxy is on its specific path, the reason for our incredible speed. It is the force that set our local group on a collision course with Andromeda, ensuring our dramatic merger in a few billion years. It has been the unseen stage director from the very beginning, arranging the scenery of our cosmic neighbourhood and pushing the actors into their proper places. Our past, our present and our future are inextricably linked to this colossal region of nothing. The simulations have given us the complete picture, the full equation of motion. The nagging discrepancies in our calculations have vanished, replaced by a clear and elegant model that works. We finally understand the forces that have guided our galaxy since its birth. We see the great gravitational rivers pulling us forward, and the vast, empty highlands behind us pushing us onward. It is a vision of the universe that is both magnificent and humbling, a demonstration of how the grandest structures and the emptiest voids conspire to create the specific reality we inhabit. We are not just residents of the Milky Way. We are residents of a dynamic, interconnected cosmic web, living on the edge of a great emptiness whose influence has been fundamental in making our corner of the universe what it is today. We have solved the mystery of our peculiar motion. We have accounted for all the forces seen and unseen. We have charted our path through the cosmos with a newfound clarity, understanding the dual nature of our journey. But this very clarity raises even deeper, more profound questions. Now that we understand the map of our local universe, we must ask, where does this cosmic river ultimately lead? What happens when we finally arrive at the Great Attractors, and what lies beyond them on the other side of the cosmic watershed in the unseen voids that dominate the far side of the universe? Our journey to understand our place is far from over. We have merely discovered the true scale of the landscape we must now explore. Our long voyage together began not with an answer but with a question. It was a question whispered by the oldest light in existence, a subtle, almost imperceptible warmth on one side of the cosmic microwave background, and a corresponding chill on the other. It was the universe's primordial echo telling us a secret we're not adrift but on a directed cosmic pilgrimage. For decades, this simple fact, our peculiar velocity, our galaxy's unexplained motion, was a grand astrophysical hood unit, a mystery written across the entire sky. We followed the clues, as astronomers have for generations, chasing the gravitational breadcrumbs left by the cosmos. Our investigation first led us to the Titans, to the great assemblies of matter that command the local universe with their immense gravitational authority. We journeyed towards the Virgo Supercluster, our home cluster's brilliant capital, only to find its pull insufficient to explain our tremendous speed. The tracks led deeper into the cosmic web towards a suspect of almost mythical proportions, a sprawling unseen concentration of mass so powerful it was dubbed the Great Attractor. It was a worthy culprit, a gravitational monster hiding behind the dusty veil of our own Milky Way's galactic plane, its true nature shrouded in mystery. For a time it seemed the case might be closed, but as our instruments grew sharper, our vision extending further, we saw that even this behemoth was not the final answer. The plot thickened, revealing that the Great Attractor itself was being pulled a mere vassal in a much larger gravitational empire. Our gaze was drawn to an even more staggering conglomeration of galaxies, a true continent of light and matter, on the cosmic ocean, the Shapley Supercluster. Here we thought was the ultimate source, the prime mover, the final destination on our cosmic trajectory. It was a narrative that made perfect intuitive sense. One of gravity's grandest creations was summoning us, pulling our local group and thousands of other galaxies into its glorious incandescent fold. And yet a nagging discrepancy remained. The math never quite added up. The combined pull of all these known structures, these cosmic leviathans, still fell short of explaining the full resolute velocity of our journey. There was a missing piece, a phantom force that was eluding our grasp. It was here at this intellectual impasse that cosmology took a courageous leap, turning the entire problem on its head. What if we weren't just being pulled? What if the most significant part of our motion wasn't a summons but an expulsion? What if the greatest force shaping our destiny was not something but nothing? This was the paradigm shift that led us here to the edge of this immense and silent sea, the local void. An expanse of staggering emptiness, a realm where galaxies are few and far between, a cosmic desert, bordering our own fertile oasis of the Laniakea Supercluster. We have spent our time together mapping its shores, plumbing its depths, and coming to terms with its profound and counterintuitive power. We have learned that this is no passive emptiness, no simple background stage upon which the cosmic drama unfolds. This void is an actor. It is a primary agent of cosmic architecture, a force of anti-gravity by proxy. It does not pull, it pushes. Imagine the universe as a vast elastic fabric studded with the heavy weights of galaxies and clusters, creating deep gravitational wells. Our Milky Way sits on the slope of one of these complex depressions, but behind us lies a region where the fabric is stretched taut and smooth, almost entirely free of mass. The result is not a pull from the front, but a pressure from behind. It's a cosmic slope, and we are rolling downhill away from the emptiness and towards the dense concentrations of matter that lie ahead. The local void is the source of that incline. Its profound lack of matter creates a gravitational watershed, expelling what little it contains and shoving its neighbours away with the relentless patient pressure of cosmic expansion. This is the secret we uncovered. Our motion is a cosmic duet, a finely balanced dance between the gravitational lure of the faraway superclusters and the persistent, undeniable shove from the vast emptiness at our back. The void is the ghost in the machine, the unseen hand that completes the equation. This discovery does more than simply solve the mystery of our peculiar velocity. It forces us to fundamentally recalibrate our understanding of the universe's structure and the forces that govern it. For so long we have been creatures of the light. Our telescopes, our theories, our very imagination have been drawn to the brilliant beacons of the cosmos, The fiery birth of stars, the luminous swirl of galaxies, the incandescent glow of quasars. We built our maps around these points of light, connecting the dots to reveal the cosmic web, that intricate lacework of filaments and clusters that gives the universe its shape. But in our focus on the threads, we neglected the spaces in between. The local void teaches us a profound lesson. The universe is a tapestry woven from both light and shadow, and the shadows are just as important as the light. Emptiness, we now understand, is not an absence of structure. Emptiness is a structure. These voids are not accidental gaps. They are a fundamental and dynamic component of cosmic evolution. They are the quiet engines of cosmic segregation, shepherding galaxies into the filaments and walls that define the large-scale structure we observe today. They sculpt the cosmos, their expanding boundaries acting like cosmic bulldozers sweeping clean vast regions of space and compressing matter into the cosmic web's glittering strands. Gravity builds the great cities of the universe, the superclusters, but the voids excavate the valleys and trace the rivers that define the cosmic landscape. To ignore them is to read only half the story, to admire the peaks of a mountain range without ever considering the immense valleys that give those peaks their grandeur. Our journey to understand the local void marks a coming of age for cosmology. It represents a maturation of our perspective, a new ability to see the universe not just for what it contains, but for what it lacks, and to recognize the power inherent in that lack. It's a lesson in cosmic humility. It reminds us that even here in our own galactic neighborhood lie structures of unimaginable scale and influence that we are only just beginning to comprehend. We live on the outskirts of a great metropolis of galaxies, but our backyard looks out onto one of the universe's great wildernesses, and that wilderness is actively shaping our collective fate. So where does this profound revelation lead us next? Our journey of discovery is far from over. In fact, the identification of the local void and its role in our motion is not an endpoint but a gateway. It opens up entirely new avenues of inquiry, providing us with a unique cosmic laboratory to probe the deepest and most persistent mysteries of existence. The future of cosmology lies not just in staring into the bright heart of galaxy clusters, but in peering into the dim, silent expanse of the voids, because it is in these vast realms of supposed nothingness that the universe's most enigmatic components hold sway. Consider the grand cosmological model we have painstakingly constructed, the lambda-cold dark matter model. It has been stunningly successful, explaining the universe from its first moments to the sprawling web of galaxies we see today. Yet it is a model built upon two pillars of profound ignorance: dark matter and dark energy. These two phenomena together constitute 95% of the universe's energy density, and we have almost no idea what they are. Voids, it turns out, are the perfect arenas in which to study them. Filaments and clusters are messy, complicated places. There the physics of gravity, gas dynamics, star formation and feedback from black holes all mix into a complex, chaotic ballet. Disentangling the subtle effects of dark matter and dark energy from this cosmic noise is an immense challenge. Voids, however, are simple. They are dynamically quiescent, dominated by the pure, unadulterated effects of cosmic expansion and gravity on a grand scale. Inside a void, the universe's fundamental properties are laid bare. Our next great endeavour is to map these voids with unprecedented precision. Future sky surveys conducted by instruments like the Euclid Space Telescope and the Nancy Grace Roman Space Telescope are designed to do just that. They will chart the positions and movements of billions of galaxies, creating a three-dimensional map of the cosmos of breathtaking scale and detail. From this map, we will not just see the voids, we will be able to study their shapes, their sizes, their distribution, and how they grow and merge over billions of years of cosmic time. This is where the secrets of dark energy may finally be unlocked. Dark energy is the name we give to the mysterious force, causing the expansion of the universe to accelerate. In the dense regions of the cosmic web, its effect is subtle, fighting a losing battle against gravity. But in the vast, underdense expanses of the voids, dark energy reigns supreme. The expansion within voids is faster than the cosmic average. By precisely measuring the shapes of distant voids, we can measure this accelerated expansion at different epochs in cosmic history. Voids are not perfectly spherical. They are stretched and distorted by the large-scale velocity fields of the galaxies around them. By measuring this distortion, a technique known as redshift space distortion, we can directly measure the rate of cosmic expansion over time. This in turn allows us to test the very nature of dark energy. Is it a constant energy of space itself, Einstein's cosmological constant? Or does its strength change over time, a phantom energy that could one day tear the universe apart? The geometry of the voids holds the answer. Then there is the mystery of dark matter, the invisible scaffolding upon which all visible structures are built. Our standard model assumes it is cold, meaning it moves slowly and clumps together easily. But what if it isn't so simple? What if dark matter has some slight warmth, some residual velocity from the early universe? Or what if it interacts with itself through some unknown force? Such properties would be almost impossible to detect in the dense core of a galaxy cluster, where gravity overwhelms everything. But they would have a dramatic effect on the structure of voids. A warmer dark matter would resist clumping, smoothing out the cosmic web on small scales and making the edges of voids less sharp, more diffuse. It would struggle to form the smallest dwarf galaxies that we expect to find orbiting within them. By studying the population of tiny galaxies that wander through the local void, or by using the subtle technique of weak gravitational lensing to map the distribution of invisible matter along its boundaries, we can place the tightest constraints yet on the fundamental properties of dark matter. The edges of voids are the frontiers where the battle between gravity's pull and dark matter's intrinsic nature is most clearly visible. Each tiny isolated galaxy we find within a void is a precious test particle, its existence or non-existence a clue to the identity of the universe's missing mass. We are moving from simply knowing voids exist to using them as cosmic calipers, as celestial particle detectors of immense proportions. This new focus on cosmic emptiness will also help us resolve some of the nagging tensions that have emerged in modern cosmology. Chief among these is the Hubble tension, the perplexing disagreement between measurements of the universe's current expansion rate and the rate predicted from observations of the early universe. Could our unique local environment be part of the solution? Living on the edge of a massive void means our local region is expanding slightly faster than the cosmic average. By precisely accounting for the push from the local void, we can refine our measurements of the Hubble constant, potentially alleviating some of this tension. Our great cosmic cul-de-sac may hold a key to understanding the entire universe's expansion. The journey ahead is one of meticulous cartography and profound discovery. We will map these hidden continents of nothingness, trace the currents of their influence, and listen for the secrets they whisper about the universe's darkest components. We are like the first ocean navigators who learned to map the world not just by its land masses, but by its great oceans, understanding that the currents and winds of those empty spaces were as vital to their journey as any distant shore. We are becoming navigators of the cosmic ocean, and we are finally learning to read the currents of the void. What began as a simple puzzle, why is our galaxy moving, has led us to the edge of a new understanding of the cosmos itself. It has revealed a universe shaped not only by attraction, but by repulsion. A structure defined not only by its contents, but by its emptiness. It has given us a new target in our quest to understand the invisible universe, a new arena in which to confront the great unknowns of dark matter and dark energy. The local void is more than just a feature on a map. It is a testament to the intricate, delicate, and often surprising balance of forces that governs all of existence. It is a reminder that the universe is still full of mysteries even here in our own corner of the cosmos, and it is an invitation to look past the glare of the familiar, to peer into the vast and quiet darkness, and to find in that profound emptiness the answers to our deepest questions. The great push away from the void is also a push forward into a new and exciting era of cosmic exploration. The void is not the end of the story. It is the beginning of the next chapter,